Good morning, everybody. This is Dr. Jingbo Louise Liu. Today, we are going to finish your Chapter 8 about the electron configuration and chemical periodicities. So today, we are going to be more focusing on the three atomic properties: the atomic size, ionization energy, and the electron affinity. Briefly, I provided a summary for you to know about the behaviors of the different elements. Last time we mentioned the different categories of the electrons. The first one called inner electrons, also called core electrons. Those are the ones which are located the same as your previous noble gases. And then the second type of electrons called outer electrons. These are the ones which are located in the orbitals with the highest energy. The third category of electrons called valence electron. The valence electrons are the ones which are involved in formation of electrons. For the main group element, they are essentially the same as the outer electrons. For the transition elements, the valence electrons include outer electrons and any n-1d electrons. So we also showed you the electron configuration of potassium and beryllium. So these two questions, I will leave it for everybody to further study. Just be careful, you have the full electron configuration and you can write it down, the configuration which is called condensed configuration. Find the previous noble metal and listed the outer electrons. The orbital diagrams, I'm more interested in the partial orbital diagrams. Also be very careful, the partial orbital diagrams, I need everybody to show the differences in the energy. 4s orbital has a slightly lower energy than 3d and then 4p. We need to see these staircases. And today we are going to start something new. We start the periodicity, three different atomic properties: atomic size, also called atomic radius, and the ionization energy, also electron affinity. First of all, let's find what is the atomic size. Atomic size, also called atomic radius. This is the measurement of your distance between the nuclei and the electrons which are located in the outer shell, in the boundary of the outer electrons. That distance is called atomic radius. This atomic radius, lots of times they can have different approaches to define them. And also because the boundary of your electron shell so cannot be very well defined. So one of the definition of the atomic size, we consider the van der Waals. Another one called the covalent. So we're going to show you in your homework exams. So three different major types of the radius. One is for your metal. Imagine, so here I have the atomic atoms for my metal, one of the atom. So you find the nuclei and then the distance between the nuclei and the boundary of your outer shell of the electrons. That's called metallic radius. So for example, this is for aluminum. Another one, if you have chlorine, they are going to form compounds, is covalent radius. Chlorine, you form a covalent compound. Covalent, in this case, is the element. So that distance, so you call the covalent radius. That covalent radius, technically speaking, is half of the distance between two nuclei of your chlorine. So you have two chlorines, they have two nuclei. That distance you call the bond, right? Bond length, that half of that one, or approximately half of it, so you call it the atomic radius. This is for your chlorine, non-metals. if you have this, say I have carbon and chlorine, so how do you determine the radius of chlorine and your carbon? So essentially you are going to, again, based on the distance, you use the distance between two nucleus as your evaluation. So your chlorine, this distance from here, from this nuclei to the boundary, and the nuclei for your carbon to the boundary. So your covalent radius for your chlorine is approximately 100 picometer pm, and your covalent for your carbon, the covalent radius for carbon is about 77 picometers. So there, the atomic size, they have different trend. Generally speaking, if you're looking at your periodic table, generally speaking, atomic size increases as the principal quantum number n increases, such as your lithium, sodium, potassium, rubium, cesium, etc., etc. You increase the principal quantum number from 1 to 3 all the way to 7. You see the atomic size increased from 37 angstrom to 270 angstrom for the different element. This is in the same group. If you have the elements which are located in the same period, so you are going to see the atomic size decreases as the effective nuclear charge increases. From the left to the right, if you take a look, generally speaking, the atomic size decreases. To make it simple, for the main group elements, transition elements, they are a little bit more complicated. This trend is much more applicable for the main group element, the ones in the A's, 1A, 2A, 3A, 4A, 5, all the way to 8A, or group 1, 2, 13, 14 to 18. So for those elements, the atomic size increases down a group in your periodic table. The atomic size decreases across your periodic table. Again, for the same group, from top to bottom, atomic size increases. For the same period, from your left to the right, decreases. So let's do a little other way to represent it. So I like this plot. You use your atomic radius in picometer as your y coordinate, your atomic number Z as your x axis. So if you have helium, neon, argon, different noble gases, so generally speaking, you see the atomic size increases with the periodic number increase. Similarly for lithium, sodium, potassium, rubium, cesium, the same trend. And if you have this same period from lithium all the way to neon, so you see the atomic size decreases across the period from left to the right. That's essential rule. But if you go to the periodic table number 5, so you see some of the elements, they show the special atomic size trend. In that case, if you are involved in the transition metals, they are a little bit more complicated. So you need to use the actual atomic size to measure it. Let's try a couple examples. The first group of examples, you have calcium, magnesium, and strontium. Second group, you have K, Ga, Ca. Third group, fourth group. So what's our plan? Find your periodic table. From now on, make sure you have your periodic table handy. And you find your periodic table, we are going to locate our different elements. And then you determine whether they are in the same group or in the same period, or they are not in the same group, same period. What's our plan? So you are going to find the common points. So for example, our group A. You have strontium, calcium, magnesium. So what you are going to find? Find the atomic size or atomic number. So we know calcium, magnesium, strontium, the first element magnesium, and then followed by calcium, and then followed by strontium. So from top to bottom, the atomic size increases. Strontium has the largest atomic size, followed by calcium, followed by magnesium. Again, they are located in the group 2 or group 2A. Therefore, the atomic size increases down to the group. So magnesium, smaller one, calcium, and then followed by strontium. Let's see these three different elements. Where they are located? They are all in the period number 4. And again, followed by period number 4, from the left to the right, atomic size decreases. K, potassium, largest. Calcium, second one. Gallium is the smallest one. And how about this C? The C, let's take a look. Your rubium. And then followed by krypton, bromine and krypton. So they are, again, those ones, they are also located in your same period. From the left to the right, decreases. The very last one, strontium, calcium, and rubium. Calcium and strontium, they are in the same group. Your rubium is not in the same group, right? Not in the same group, not the same period. In this case, so you are going to find the common points. Strontium is slightly smaller than your rubium. Your calcium and strontium, they are in the same period. Strontium and rubium, they are in the same, strontium and calcium in the same group. And then your rubium and strontium, they are in the same period. So rubium bigger than strontium, strontium bigger than the calcium. Again, in the same group from top to bottom, size increases. The same period from left to the right, the size decreases. The second important atomic property is called ionization energy. In terms of the ionization energy, we need to know what's the definition. And also we need to know what is the trend. Again, I like this plot showed you the trend. It's simple for us to generalize this. Generalize the ionization energy is essentially opposite to the atomic size. The trend is opposite to the atomic size. First of all, let's see what's the definition. The ionization energy can be abbreviated as IE. IE is the energy required for the complete removal of 1 mole of your electrons from 1 mole gaseous atoms or ions. Remove 1 mole electrons from 1 mole gaseous atoms or ions, you need energy. That energy in kilojoules is called ionization energy. The atoms with low ionization energy normally tend to form cations, such as your group 1, group 2, the metals. The atoms with high ionization energy tend to form anions. Most of the gases are non-metal elements except noble gases. Your noble gases, they stay as itself. Normally, they do not gain electron or lose electron unless you have a special condition. Ionization energy tends to decrease down your group. In the same group, ionization energy decreases. Ionization energy tends to increase across a period. In the same period, for example, from lithium to neon, ionization energy, generally speaking, increases, but they have lots of exemptions, such as lithium, beryllium. Beryllium is bigger than aluminum, and the nitrogen is bigger than the oxygen in terms of the first ionization energy. So we need to be slightly cautious. And then ranking. We have 4 different groups of elements. So how do we rank those elements? By the first ionization energy. The first ionization energy is the energy required to remove 1 mole of your first outer layer electrons. So from 1 mole of gaseous atoms or ions. So our problem is use your periodic table, determine the ionization energy in the order of decreasing trend. What's our plan? Again, find the periodic table, find the element location in your periodic table. The same group decreases from top to bottom. The same period increases from your left to the right. So let's see our solution. For your first group, let's see, helium is the top, and argon and krypton. So therefore, they are in the same group from top to bottom, decreases, yes. And then the second group B, the group B, all of these 3 different elements, antimony, tellurium, and tin, they are in the period number 5. From the same period, left to the right, ionization energy increases. I write it down IE1. This number 1 represents the first ionization energy. Let's see. Group C, calcium, potassium, and rubium. How do you determine it? Let's see. Calcium and potassium. Calcium, potassium, they are in the same period. Potassium and rubium in the same group. So same group, potassium bigger than rubium. Same period, potassium smaller than calcium. Therefore, the ranking will be calcium, potassium, and rubium. The last one. So this Xe is your noble gas. Noble gas usually has the largest first ionization energy. And then compare these 2, iodine and cesium. Iodine and cesium, which one is bigger? So iodine is a non-metal, gains electron. Cesium is the metal, loses electron, lower ionization energy. So therefore, noble gases followed by non-metal, followed by the metal. And then the last point, actually we do have 2 more points. So we also have some sides which they are for the ions. First one, if you have cations meaning losing electrons. Those cations has a smaller size compared with their parent atoms. If you have your anion, the anions going to have bigger size compared with the parent atoms. Cation loses electron, anion gains electron. The ionic radius, so does follow the same trend as the parent atoms. Ionic radius increases down a group as your N increases. From top to bottom, the ionic radius increases. The cation decreases as the charge increases. If you have positive 2, positive 3, the more positive, the smaller the size. Therefore, we are going to learn one more term called isoelectronic series. Those isoelectronic series is the different species of the ions. and they have the same electron configuration. So within the series, the ion size decreases with the nuclear charge increasing. If you have positive 3, losing 3 electrons, something losing 2 electrons, so the one which is more positive will be smaller. If you have 3 negatives, 2 negative, the one more negative, the size will be bigger. Now let's ranking couple different ions. So we have this group A, and group B, and group C. Group A, what's our plan? Find the position of your elements, determine whether they are in the same group or the same period. If they are not, are they isoelectronic, or are they same element but losing different electrons? Let's see the first group. The first group, magnesium, calcium, strontium, they are located in the group 2 and group 2 or group 2A. Therefore, the ionic radius is going to be decreases from bottom to top. You can say increase down the group. So magnesium smaller than calcium, smaller than strontium. Sulfide, chloride, and potassium, they are the isoelectronic. So sulfur 16 plus 2, 18 electrons. Chlorine 17 plus 1, 18 electrons. Potassium 19 electrons. Minus 1, 18 electrons. All of these 3 ions, 2 anions, 1 cation, they have the same electrons. They are called isoelectronic series. Therefore, you are going to determine the nuclear charge. Which one has the bigger nuclear charge? And yes, sulfide. Again, you can use the positive, negative. The more negative, the bigger. The more positive, the smaller. So 2 negative bigger than 1 negative, bigger than positive. And the last one, the same gold species. The parent is gold metal. So the more positive, the smaller. So cation decreases in the size as the charge increases. That's essentially about the size changes. And then we have one more term called electron affinity. You can use a capital EA to represent electron affinity. Electron affinity is the energy change. One mole of electrons is added into the 1 mole of gaseous atoms or ions. This electron affinity has the same trend as your ionization energy. The atoms with low electron affinity, such as those metals, tend to form the cation. The atoms with high electron affinity has a potential to form anions, meaning gains electrons, such as your gases, except your noble gas. The trend in the electron affinity very similar to the ionization energy, but you do see some irregularities. So they are not as regular as the atomic size or the first ionization energy. In that case, you do need the real value, but generally speaking, in the same group from top to bottom, electron affinity decreases. In the same period, electron affinity, generally speaking, increases except the noble gases. So up to this point, I'm going to summarize using 3 different graphs. So if you have the atomic size, down the group increases, cross the period, decreases from left to the right, or otherwise from your right to the left increases. On the opposite side, if you have your ionization energy, so ionization energy decreases from top to bottom. Ionization increases from left to the right in the same period. Your affinity of electrons, electron affinity is not as regular as the two properties, atomic size and ionization energy, but generally speaking, in the same group, electron affinity decreases from top to bottom, or from bottom to top increases. In the same period, from left to right, shows the increasing in the electron affinity, but remember, there are lots of exemptions. Your metals, they tend to have low ionization energy, low affinity. Metals loses electron, form the positively charged ions, cation. Your non-metals, if they are reactive, they tend to have high ionization energy and highly negative electronegativity, meaning they love electrons. And then the element attracts electrons strongly, tends to form negatively charged ions. And if you have noble gases have high ionization energy and the electronegativity is slightly positive, those elements tend to neither lose or gain electrons. These noble gases, they stay as themselves, neither lose nor gain electrons. Up to this point, I've finished the lecture. Thank you so much for listening. Stay safe, stay healthy.